Hello, everybody. Welcome to Sea Star and Exploragens presenting this week's Planetary Science and Astrobiology seminar. This is the kickoff of our Space Science at Tech Week. So there will be a whole, actually 8 days of exciting events planned in order to celebrate the Perseverance rover's landing on Mars. Hear about just in a moment, as well as showcasing some of the science that's happening here at Georgia Tech. As well as the engineering. So without further ado, I'm going to introduce our newest member of the Planetary Science faculty here at Georgia Tech, Dr. Frances Rivera Hernandez, to introduce our speaker.
Yes, thank you, Brittany. And today I'm super excited to introduce Dr. Aileen Yingst, as Brittany said, to kick off our Space and Science Week at Georgia Tech. Dr. Yingst is a planetary geologist and a senior scientist with the Planetary Science Institute. Before her current position, she received a bachelor's from Dartmouth College in physics and astronomy, and then went to Brown University, where she completed a master's and PhD in the geological sciences. She's been involved in a lot of NASA missions to Mars, including Pathfinder, Mars Polar Lander, Mars Exploration Rovers, Curiosity, which is how I know Aileen, where she's the deputy principal investigator for the MAHLI camera, and she's also a co-investigator for the Mastcam, MAHLI, and MARTI cameras as well. She's also now a co-investigator on the SHERLOC instrument on the Perseverance rover. She's also the PI for the Lunar Heimdall camera, participating scientist on the Dawn at Vesta mission, and she conducts a lot of fieldwork on Earth to design and optimize rover operations strategies for missions, and a lot more that I probably did not mention. She truly is a role model for me and a lot of us in the community. And so today she'll be talking about, of course, Perseverance, in particular, how we can use the Perseverance rover to learn about the geology of Mars. And so, which of course it's going to be landing next week, and we're all super excited. And so thank you, Aileen, for talking with us today, and take it away.
Thanks very much. I am humbled by that. I first want to let everybody know that if I turn my video off, you're probably all aware that we're all at home, and so if things start to get a little choppy, I'm going to look to one of my hosts to let me know that that's the case. And I'll turn off my video. I know Frances from working very closely with her on the Curiosity rover. She is a brilliant scientist, and I just want to point out that Georgia Tech is very lucky to have her. I know Brittany from the Dawn mission, where we work together to get the best data from Dawn from the minor planet Vesta, and Georgia Tech is also very lucky to have her. I just wanted to point that out. So I will go ahead and get started. If I could see the first slide, see if that'll show up. Okay, right now it says I'm in the event, but I'm not seeing any video. So I don't know. If everybody else can see the slides, I'll just continue, Brittany, so let me know one way or the other.
Yeah, can I, sorry, since I'm doing both, can someone just verbally confirm, one of our presenters, that you can see my screen? So we should be seeing...
Okay, I can see your screen now.
Excellent. Now let's go to presenter mode. That should be slide sorter view, right?
Yes.
No.
No? I see 2 slides.
Cool.
There we go.
Now I see 1.
All right, sounds.
Thank you.
Yeah.
And I very much appreciate you going ahead and running the slides for me. So without further ado, yeah, go ahead and go to the next slide, because that's just a title slide. So I don't think it's surprising to this group that we're interested in Mars. I'm going to assume that I have sort of a mixed bag here. General interest, everything from general interest up to perhaps experts. Certainly, I know I have some experts because my hosts are experts. So I'll try and kind of hit all of those audiences. I think we're all here because we understand the importance of Mars as it is becoming a place. That is, these pictures, this one in particular, I think, of Dingo Gap is very evocative of Mars as a place that's familiar and yet unfamiliar. And as a geologist, and as a human being actually, but as a geologist, that is very compelling to me because it tells me that here is a place where we can learn something very fundamental. We can learn very fundamental things about how planets form and how they evolve, because we have a planet that has many things that are like Earth, many things that might once have been like Earth, but now are very different. So Mars is now a cold desert, certainly colder than Antarctica, certainly more of a desert than Antarctica. So why is it that we are excited about Mars? So if I can have the next slide. This is one of those sort of very evocative pictures as well. On the left, you have orbital mosaic of modern Mars. On the right, you have an artist's conception of what Mars may have looked like 3.6 billion years ago. And that's one of the really exciting things about Mars. When you look at it, you're looking at a planet that may once have been habitable. And what do we mean by that? We mean that in Mars' distant past, it may have had the environment, the conditions, the initial conditions that would have been amenable to life arising and thriving. And that has profound implications for astrobiology, for what it means to be alive in our solar system. But I'm going to focus mostly on geology because that's my area of expertise. And in that too, Mars is a very exciting place because it retains much of that record of the early solar system. It retains much of that record of a time when both Earth and Mars together, you might have had two potentially habitable planets in the same solar system. So if we could go to the next slide. This is just to remind us that the oldest rocks on Earth are relatively young in sort of a solar system way of looking at it. You can see in the gray rocks that are 2.5 billion years old, and a couple of places on Earth where rocks are older than 3.5, 3.6 billion years. Those places are few and far between, and if you are looking at those yellow dots, you can see that they're also relatively hard to get to. But it's an important, and I'm just going to turn off my video here real quick because I'm getting a little jumpiness here. It's an important point because by 3.5 billion years, we have evidence of life on Earth. So at that point in the solar system's history, you have life not just having had arisen, but leaving records in the rocks. But Earth has, as many of us know, plate tectonics. And for those who are coming in as a general audience, all this means is that if most volcanoes on Earth, most earthquakes on Earth, most places where the Earth is very active geologically are places where two plates, two pieces of the continental or the ocean, two pieces of the crust come together. They're either pulling apart, they're sliding past each other, or one is going, or they're knocking into each other. And when that happens, of course, chaos ensues, but it also means that the rocks on the surface of the Earth are being constantly recycled, not just by the weather, which certainly happens, not just by running water, which we see in in sort of an immediate way, but in this long-term way where rocks can actually go right underneath the crust we're walking on and be completely recycled, and then, you know, later on come out, those minerals and volatiles can come out in a volcano many hundreds of miles away. What that means is that the surface of the Earth, most of it is relatively young. And so if we want to look back at those points, those very early points where life arose and started to thrive and really take hold, it's tough to find those places on Earth. On the other hand, Mars has most of that time period still recorded in its rocks. We're going to see that although Mars has evidence of liquid water having been on the surface, and in some cases a lot potentially of liquid water, it still has very ancient crust. There's a reason you have huge basins, right? Impact basins, craters on Mars that are retained in a way they simply are not on Earth. They're retained in a relatively pristine way. What that means is that we have something that's unique on Mars. It's what a habitable planet looks like in its infancy, in a very early point in solar system history. That's a record that we really don't retain on Earth, but we still have it on Mars. So if I can have the next slide. So that's interesting to me as a geologist. The older the rocks I can look at, the further back in time I can look at. But it's also important for astrobiology. And the simplest reason is that if we're going to be looking for life arising on Mars, right? What should we be looking for? Well, we have seen a couple of things here. We've seen that Mars was once warmer and wetter and was able to sustain liquid water on the surface. And some places standing liquid water. And we're going to be talking about some of that evidence in a minute. But that it's no longer the case. So for those in a more general audience, why is it that we're not looking for dinosaur fossils? Why aren't we looking for even, you know, tiny animal fossils? Why are those not things that we are searching for? That's because if we have to look at Earth as our guide, and that's the best we can do, because that's really our only example of life rising and thriving and growing and so on. Then if we look at the biological timeline for Earth, that arrow shows you where that climate change occurred, where Mars started to get less habitable, where it became not such a nice place to be if you were life. So how far did life, and nobody should apologize, speaking of life, just right now, no one should apologize for life intruding in this talk. So if your kids or your pets or whatever have decided to join us, don't worry about that. They are welcome. We are all in this together, and we're all just let's assume that we're all sitting around, you know, with our cup of hot beverage, enjoying a discussion about Mars and the fact that we're about to have a rover on Mars, which is totally cool. So again, this is the terrestrial biological timeline, and what this tells us is that if you kind of assume that that you had two habitable planets, and this is an assumption, that you had two habitable planets, that the climate change is that point where life is going to be spending its time trying to survive, not becoming more complex. So what that tells us that in the first billion years on Earth, life had gotten only as far as the microbial stage, and if that happened on Mars as well, we shouldn't expect to find anything more complex than that. So if I could have the next slide, please. What that tells us is that we should not be looking for the super complex stuff. We should be looking for what we often refer to as biosignatures, right? Biosignatures. What does that mean? So on the right, on the left, those look like traditional fossils. On the right, what you're looking at is what's called that's a fossil of what's called a stromatolite. And a stromatolite is produced by microbial mats, right? So you've got shallow water, and these organisms, these very simple organisms, grow together in a colony, and they leave behind these microbial mats, and they can be fossilized. This is something that we would declare victory if we saw on Mars. And I'll just show you a couple pictures of stromatolites. I'll take the next slide, please. Just to kind of give you an idea, this is an area called, on Earth, obviously, at Shark Bay. So the lumps that you're seeing in this picture are made by life. So you could picture something like the Great Barrier Reef, where coral builds up these formations. These are actually much simpler forms of life than the animals that build up coral reefs. And these are built by single-celled organisms. These are built up by microbes that will form these colonies of these microbes on the seafloor. And you'll see the tide going in and out, and these microbes kind of building up their habitats. Next slide, please. If you fossilize them, they look something like what you'll see in the next slide. Oh, there it is. Great. I guess I'm a little slow on my end. This is what they look like, and you can see a Sharpie pen on the right there for scale. Again, we'd be cracking the champagne if we saw something like this on Mars. But pound for pound, this is actually a pretty complex form of life as well, and we're not necessarily expecting to see even this. But what we can do is kind of take a look at the range of biosignatures that we have from Earth and see what we might look for when we're on Mars. So if I could have the next slide. And again, biosignatures is just a fancy schmancy way of saying what evidence might life, even simple life, leave behind. It might leave behind fossils, right? Like the pictures on the right. Again, more stromatolites. It might leave behind evidence of its waste products. It might leave behind evidence of the molecules that build up that life. So, excuse me, one of the ways you know, right, if you're an alien coming in looking at Earth, one of the ways you might know that there's life on Earth even before you get here is if you took a spectrum of the atmosphere and saw some of the waste product that life gives off. So these are the sorts of things that Perseverance might be looking for, and they're hard to find. So the best thing you can do, the best way you can increase your chances of finding something this small or this difficult to detect is to go someplace where if there was life, there might have been a lot of it. Or if you're looking for a place that life would have light, that would have been habitable, you would go someplace where it was like really a happy place to be, and life would have a long period of time, in Mars terms, a long period of time to live there if it ever existed. So if I could have the next slide, please. So I'm really here because the Perseverance rover is slated to land, and if anybody has wood to knock on, if you're superstitious, go ahead and do that now. Is slated to land on Thursday, February 18, at Eastern Time, 3:49, I think is when the landing cycle starts. That's why we're here today, because we're actually going to be looking for habitability and potentially signs of ancient microbial life. So this is the official set of objectives for Mars 2020, which is the mission. Perseverance is the name of the rover. So you might hear me use either of those terms, Mars 2020, which is the overall mission, or Perseverance, which is the actual physical rover. So here are the Mars 2020 objectives. We want to understand the geologic context, the geology of the area that we intend to land in. We want to understand the astrobiology, identify any astrobiology, should it exist there. If it does not exist, have an understanding, a better understanding of why that's the case. What's missing in our understanding of what makes a habitable place? Is there anything missing there? If so, when was it missing? And I'm just going to remind everybody that geology is sort of a four-dimensional thing. You have to look not only at 3 dimensions, but also remember that you're looking backwards in time often as well. And then objective C, sample caching. We want to bring some of those interesting Mars rocks back to Earth. And to do that, we're going to put it in a little cache, C-A-C-H-E, for later return to Earth. And then, of course, at some point, we want to be able to go to Mars. And there are instruments on the rover that are meant to further that goal as well. So if I could have the next slide. This is the rover with all of the different science instruments. These are the ones that I'm most interested in. You also, of course, have the rover chassis itself, which is very similar to the Curiosity rover. The instruments are different. In some cases, they're very different. But the chassis itself should look familiar to those of you who've seen pictures of the Curiosity rover. Next slide, please. So we'll just take a couple of minutes here, kind of go through the instruments so you have an idea of what the capabilities are, what the rover can do, and of course, in the back of your mind as well, what it can't do. And so you'll see a picture on the left-hand side of the actual instrument that I'm talking about. On the right-hand side, that's an outline of the rover, and you'll see where the instrument is in yellow. And so oftentimes you'll see what you're seeing in this picture. You'll see, in this case, we're talking about Mastcam Z, which is a pair of cameras that look out in stereo to the surface. They have the ability to zoom, so you can take, you can kind of get closer up, further away. It can also take high definition video, which is going to be pretty exciting on Mars. But you'll note here that there are spots on that sort of right-hand image that seem to be far away from the camera. Those are things like the DVR recorder, power sources, that kind of thing. As we go forward, that's why you're seeing instruments in kind of multiple places, because you'll have the cameras, but then you also have to power those cameras. So Mastcam Z is what it sounds like. It's a pair of cameras, stereo cameras. They're in color. They also have some filters that allow us to look in other parts of the spectrum. Those other parts of the spectrum are important in trying to identify certain, what we believe are common or interesting minerals. So for example, if you are a rock that has iron in it, your spectrum may have a little dip in it. It has an absorption band around 1 micron. And if we can measure the spectrum at around that area, we can say, oh, look, there's a little dip there. That means we probably have some iron in this rock. So that's why these cameras have some filters as well. Next slide, please. SuperCam, right next door. So that big sort of eye-looking thing, that's SuperCam. This is a laser spectrometer. And this does something very similar to the ChemCam instrument on Curiosity, and that is that it zaps rocks. And we then measure the plasma that comes from that laser zapping of rocks. It sounds a little space-agey. But the idea is basically that it is easier to measure a plasma or a gas from a distance than it is to measure the specific content of the rock. So for example, with Mars Pathfinder, the little Sojourner rover would actually have to get right next to that rock and pretty much come in contact with it to get an idea of what it's made of. But if you can turn the different minerals and elements in that rock into a gas, it's relatively, it's far easier to measure it from a distance. And so that's what SuperCam does. Next slide. Now I'm going to talk about 3 instruments that are on the arm, the turret of the rover. It has a 2-meter arm on it. I'll start with PIXL, and this is one of those times where I'm just going to take a moment to be curmudgeonly. This is my one curmudgeonly thing, and I'll even turn my camera on so you can see me looking grumpy. Hold on. So what you'll see as we move forward here is many instruments that are named as acronyms. I am not a big fan of acronyms because I don't find them particularly explanatory, and sometimes they can be torturous. And we'll run into that in just a second. Down off the soapbox, the PIXL instrument is basically X-ray fluorescence. So at sub-millimeter scale, so that's very close, sub-millimeter. So a millimeter, you can pull out a ruler and see how big a millimeter is, but we're talking, kind of human hair thickness when we're talking about PIXL. It will focus an X-ray beam to a very tiny spot on a rock or onto the regolith, the broken up, sandy, soily, whatever. I hesitate to use soil because there are no organic components, but the regolith, the broken up rocks of the surface, and analyze the X-ray fluorescence that comes off that to understand what that target is made of. Next slide, please. The SHERLOC instrument uses deep UV Raman and fluorescence spectrometry. It has a relatively small spot size, just like PIXL, so you have to kind of get right up there. But that also will help us understand fine-scale mineralogy, and it will help us detect potentially, if they're there, organic compounds. And that's, you've learned now, important for this mission. So next slide, please. And here's one of those torturous acronyms. Watson is part of the SHERLOC instrument. I'm sure that startles you. Watson is a context camera, essentially, for SHERLOC. So you're taking a very tiny bit of real estate when you're taking samples from SHERLOC or PIXL. And Watson allows you to get sort of a context image. And that still is a pretty small image. It's maybe the size of a postage stamp or a couple of postage stamps, depending on how far away that image is being taken. But it does give you much broader context of saying, all right, I'm getting a spectrum from this point. Here in this bigger picture is the point that we're looking at. So it's probably that grain or that mineral there. Next slide. And this just gives you an idea of how those 3 instruments work together. You can see sort of a Watson scale image on the left. The first is in the field. That's a stromatolite in the field. And then the lower image is a cut rock face. And then those little boxes there, the box on the top, the one that's square shaped, those are SHERLOC scans of different minerals, and then below that are PIXL scans of the longer box. Next slide. Some other instruments, RIMFAX. This is essentially ground penetrating radar. It allows us to look underneath the surface to be able to figure out what different layers might be underneath the surface that are giving expression on the surface. So next slide. MEDA is our weather station, and MEDA gives several parameters of the atmosphere, including wind speed, wind direction, pressure, humidity, air temperature, ground temperature, and radiation, as well as the optical properties of the dust, which is very important on Mars because dust is ubiquitous, and you really need to know how much dust you're looking at and looking through to be able to understand what's past that dust. Next slide. The MOXIE experiment is a technology demonstration. So if you want to send humans to Mars, one of the most efficient things, if you can figure out how to do it, is to use the stuff that you find in situ instead of bringing all of the stuff you need to survive. This is one of the first experiments that will allow us to see how we can do that. So it collects carbon dioxide from the atmosphere and then splits those molecules into carbon monoxide and O2 into oxygen. And obviously oxygen is going to be a very important resource to have on Mars. And so this is one of the first steps in that objective D, getting humans to Mars. Next slide, please. One of the sort of late-breaking things about Mars 2020 is that it will be a caching mission. So the overall highest priority of Mars science in the last several decades has been to return samples, well-characterized samples, well-chosen samples from Mars to Earth. And Perseverance has been turned into the first step of this Mars sample return. So if you see MSR, that's Mars sample return. And this is the current caching strategy. That is, the rover will, within its primary mission, go to some regions of interest, choose a site, and drop off its caches. If it is then able to have an extended mission, it will have a location where it can go back and drop off more cached samples, so that in the future, a very efficient way of picking up those samples is simply going exactly where the next spacecraft needs to go, picking up the samples, and coming home. And so Perseverance is the first step in that. Next slide, please. Mobility system, that's just a fancy way of saying the wheels and the suspension. There are some small differences between the Curiosity wheels, the one you'll see on the left, and then the Perseverance wheels that you'll see on the right. They're just slightly larger diameter, but just a little bit narrower. And you can see that the cleats on the wheels have been redesigned in part. If you'll look at some of the pictures of the Curiosity wheels, you can see that the very sharp rocks on the surface have kind of eaten them up. And the wheels have been redesigned just a little bit to hopefully kind of have those cleats push some of the smaller rocks out of the way, or to push them into the ground a little bit better, so that we can have a little bit longer wheel life. Next slide. These are pretty pictures. These next couple pictures here are pretty pictures. This was taken May 28 of last year. We were in the middle of the pandemic. So this is kind of a victory photo as far as I'm concerned, that this actually occurred and occurred safely. So the next time you see the various parts of the spacecraft, they will be about 6 miles above Jezero Crater on Thursday. Next slide, please. Again, a pretty picture. That's the stack together being put into the nose cone. And then the next slide will show the launch pad and the launch of the rocket mid-July. The next slide, just an artist's conception of what crews would look like. But the next slide, and we'll see if it actually runs. Oh, look, yay. This is a new landing technique where you are able at a certain distance to take descent photos. That is, we have orbital photos, but the closer we can get to the surface, the better chance we have of picking up those meter or less obstacles that might cause us problems in landing. So you can take some descent photos at better than orbital resolution and compare it to the orbital map. and divert if necessary. We hope it's not necessary, but this new landing technique does give us that capability. So next slide, please. A little bit about our landing site and why it's so exciting. This is where Jezero Crater is located. And for those of you who are not used to seeing this kind of image, this is a topographic map of Mars. It's the entire surface of Mars kind of rolled out like it's on a sheet of map paper. The lower areas are in blue. The higher areas are in red and gray and white at the very top of the scale. Jezero Crater is right at that crux where you start getting in this very low-lying flat area. If you ask some scientists, they'll tell you that this was once completely filled with water. There's some disagreement on that, depending on who you ask, but it's certainly an area that is far flatter. It was clearly far wetter. And whether or not it was sort of a hemispherical ocean, there was certainly water there, much more abundance than in other areas of the planet. Next slide. Here's some context. Jezero Crater is right on the edge of the Isidis Impact Basin, a very old 3.9 billion-year-old basin. But the really interesting part, I think, is the next slide, which closes in on that crater. So if I could have a, yes, thank you. This is Jezero Crater. That ellipse that you see is the potential landing ellipse. And you can see here all sorts of channels that empty into Jezero Crater. And if we could see the next slide. This is the really exciting thing. These are what we believe to be delta deposits inside Jezero Crater. And you can see some of the interesting minerals that we can identify from orbit in the color-coded map on the right and on the left. It's another one of those topographic maps, digital elevation models. That's what DEM stands for. What you see here is essentially a hydrologic system where you have inlet valleys and outlet valleys, and an area where we believe flowing water came into the basin, and then because of the difference in elevation, rapidly lost velocity and dumped its sediment load quickly. And that's what you see in a delta. So if I have the next slide, why do we care about deltas? Deltas are habitable environments. You have lots of water, you have lots of potential nutrients that are being dumped in one place. The water can be relatively quiescent depending on what type of delta it is. So there's not a lot of churning around of fragile organisms. So we're all, this was a community choice, and we're all pretty darn excited about going to Jezero Crater. Next slide. This is obviously on Earth. This is a runoff delta in Alaska, but again, something that might not have been too far off of what Mars looked like and why this area is so exciting. So if I could have the next slide, I'm just going to take a couple of minutes for my own vanity here to talk a little bit about the kind of research that I hope to be doing when we end in a week. This again is the Watson camera with its somewhat goofy acronym that nevertheless spells Watson, which is good association with the SHERLOC instrument. Not only is it meant to be a camera that documents for SHERLOC, if I could have the next slide, it is a research and science instrument on its own. It is going to serve as a magnifying glass for studying small grains on the surface. And so on the left, you'll see the predecessor of Watson, which is the MAHLI camera, which is the one that's currently running on Curiosity. And on the right, you'll see a test image that was taken for Curiosity. And this is the type of image that we expected to get from Curiosity and did. I'm going to show those in a few minutes, and that we hope to get from Watson. So if I can have the next slide, please. Why do we care about little grains? Because grain characteristics, grain relationships, and the structures in that sort of 0.5 millimeter to 10 millimeter scale tell us something about the environment in which those grains formed. Both how the rocks themselves formed and also how they were modified afterwards, how those grains got kind of knocked off of whatever outcrop they were on and worn down and moved, and whatever happened to them, they retain that record. So textures captured by Watson, and by textures I mean, what does the grain look like? What shape is it? How big is it? What does its surface look like? That will tell us something similar to what you might expect a geologist would see in the field using a hand lens. So we hope to see a range of characteristics, all of which are going to tell us something about the lithology of the rocks at the area. So next slide, please. I'm just going to remind you that these are from Curiosity. They're from Jezero Crater, and they were taken by the MAHLI camera, which is Watson is essentially a build-to-print MAHLI camera. So the cameras should behave the same on Mars, or very similarly. This is again Gale, not Jezero, but it should give you an idea of what kind of things we expect or hope to see and how the Watson camera might perform. Next slide. This is what we call the sheepbed member, and what you're seeing here is a range of resolution, sort of nested resolution. So if the arm is, say, 1 meter from the surface, we'll get that first big picture. If it's down to 5 centimeters from the surface, you'll get that next one, and then the tiniest one inside is when the arm is brought to 1 centimeter or 2 centimeters from the surface. You can see that scale bar there giving you an idea. On the left, that scale bar is 4 centimeters. On the right, that scale bar is 5 millimeters. And this particular picture is interesting because it shows that in the Jezero Crater area, you have mudstones. You have silt-sized grains. Now, the MAHLI camera and by extension the Watson camera, they're both designed to a specific resolution. So they can resolve somewhere around 15 microns per pixel. What does that mean? It means that if you are in the sand-sized grain bucket, those cameras can resolve you. If you are smaller than that, in the silt size or smaller bucket, you are below resolution. Why is that important? Because silt-sized grains and smaller are what you'd expect in, say, a lake environment, in a place where those tiny grains can settle and create these very, very fine-grained fine stones, if you will. That's why this particular image is so exciting, because this is the MAHLI camera on the Curiosity rover basically not resolving grains, which tells you that this is a mudstone, which tells you that this is potentially a lake environment. Next slide. This is an area called Gillespie Lake. It's not an actual lake. It's named after Gillespie Lake on Earth. But this, again, gives you an idea of the range of grain mixes and grain sizes and grain morphologies that we've seen at Jezero Crater. And we're hoping that we'll see something similar at Jezero. Next slide. You can see the difference between these two targets. One has far more of the, or this one, it's probably easier to say it that way. This one has far fewer of those larger grains, easily resolvable grains. It's a much finer stone here, but you can also see the directional laminations here. Next slide. And this is actually one of my favorites. This is an area called Barden Bluffs. And those arrows show places where you have grain-to-grain contact. And that black arrow shows a place where we think that little divot there has been knocked out by another grain. And that sort of class-supported matrix suggests a conglomerate, that is, another rock that requires water to form. So next slide. What will Jezero show us? This is a sort of a oblique angle image of our landing site, and we are just terribly, terribly excited to get there. My last slide actually shows sort of the, what they plan to do for Mars sample return, and we can certainly go there. But what I'd rather do right now is just sort of open it up for questions, comments. I'd certainly be happy to answer anything in the chat window as well. I want to make sure I have enough time to answer some questions. So why don't we go ahead and do that?
Thank you so much, Aileen. Yeah, if anybody has questions for our speaker, feel free to unmute. I think we have that capability. If not, feel free to write it in the chat. And thank you again for a great talk.
Hi, Aileen. This is James. Can you see me? Or
I can. Yes.
Hi. Thanks for a wonderful talk. As you, as a veteran of these missions, know, they get so much attention in the first days after landing, but realistically, there's always a period of engineering checkouts, essentially, for the mobility system and the instruments. And so I was wondering if you could just sort of help set expectations for how things will likely unfold over the coming weeks and months.
Oh, what a wonderful, wonderful question, James. Thank you so much. So James has outlined very beautifully the fact that these are very complex spacecraft. The rovers are very complex. They have, tens of instruments, depending on if you're going to count every single one of the engineering cameras and so on. There's a lot going on here. We want to make sure that if you're using instrument A, it's not going to somehow talk wrong to the spacecraft and thereby make it impossible for instrument B to get its own commands and so on. There's a very there's a planned out sequence of events that will occur, and those will occur. The most critical ones will occur in the first 4 Martian days, which we call sols. So the first 4 Martian days, we'll be getting images down. We'll be getting some data down. But most of that time is going to be commissioning, or not even commissioning, just, safety checks. After that, we're probably looking at another 15 to 20 sols we have a flight software boost that we have to do in the next 4 sols, so through sol 8. And then we have, then we start out the instrument commissioning phase. And in that period, the idea is to pick a spot for the rover where we're not going to be able to move after about sol 30 while the helicopter does its thing. And that is that's a technology demonstration. And so it has to be far away and not in our way and not, having any kind of risk of flying back into the rover or anything like that. So there'll be a helicopter checkout and activities, and that I think is another 30 sols. But that will be a time when the rover, although it can't move, will be able to do some science. But the commissioning phase will probably be. You can start expecting regular operations within 60 to 90 sols, but you'll be getting data the very first sol. And it will start trickling down within the first 4 sols. And by, say, sol 10 to sol 20, we'll start to get some information that will tell us how much activities we can do. And starting about sol 30, I think those commissioning activities will start making us feel like we've got science coming in.
Very helpful. Thank you.
There's a question here from Aaron Patel who says, how do other deposition mechanisms like wind-blown fines affect grain size investigations on Mars?
I'm I'm struggling not to say my visceral reaction, which is I hate dust. It's always in a way, but that's not the case. At least for me, when I am looking at grain morphology, and I could see Frances smiling as well. She's like, dust. Because it's so fine-grained, it really can cover everything. And so we have found interesting ways to try and clear off the dust for the targets that we're looking at. And of course, on Curiosity, we have the dust removal tool, and on Perseverance, we will have a gas dust removal tool. It'll poof, blow things off. On Curiosity, we have in the past actually used the ChemCam laser because it creates a little bit of a poof as well and kind of blows away some of the dust. But if you're trying to look at very fine grain scale morphology, it is in the way. There's no question. And what you want to do is try and get rid of it as best you can. It's one of the reasons that dust storms, unfortunately, for the spacecraft, dust storms aren't necessarily great. But after a dust storm, everything's clean, and so it's a great time to be, the looking at the fine-grained rocks.
We've got another question, which is outside of compositional indicators of organics, what kind of geologic observations would prioritize a rock for drilling or caching? From Justin Lawrence.
So there are two objectives at least, and I want to be real careful about what you might be looking for in a rock in terms of astrobiology, because that's not my area of expertise. If I'm on Earth, I'm typically looking for very, very fine scale laminations that might indicate the stromatolites, which again pop the champagne, but also places where biominerals might congregate. But remember too that there's objective A, which is actually the geology, and so the number of samples that we're looking at are not just find the 5 best places that might have been habitable or might have evidence of biosignatures. The idea is to get a full complement of samples that tell you what the geologic system was in that area. So there are tubes that are meant specifically for old basalts, for example. There's plenty of basalts on the floor of Jezero Crater, and that's part of the stratigraphy. That's part of the story. There are plenty of tubes that are set aside to be able to tell the full story. So I'd hesitate to say this is precisely what you're going to be looking at, because each one of those stratigraphic layers is going to have its own set of criteria.
Before I ask another question, I'm going to take Chair's prerogative here and ask if you would explain the signs that are over your shoulder there. It says Myrrh and Sol, also nice on the other side.
Oh, okay. Let's see. There you go. Over here?
Yeah, you've got your Myrrh and Sol. Yeah, there you go.
Okay. So every in the JPL IST, and you know what, you use acronyms so long you forget what they stand for. That was the room where we did the sequencing for Spirit and Opportunity to keep track of what day it was, because your calendar on Mars is different than your calendar on Earth. They would post these Myrrh A, which is Spirit, and this was the Sol. So we did 2143 and 2144 would have been a 2-Sol plan. That's why they're stapled together. And so they're all signed by many of the engineers and scientists who worked on the MER rover. And then on the other side, on the top, there's a panorama from Pathfinder, and on the bottom, this is one I'm particularly proud of actually, is a self-portrait taken by the MAHLI camera of the Curiosity rover. That was sort of our gift to the public who funded our mission, a postcard from Mars.
Amazing. So Oscar Klempe asks, were there any science instruments you wish could have been included but weren't able to fit due to budget or science or space or weight constraints?
Certainly budget is the big one. Typically not science. We'll get as much science as we can, but weight is an issue, volume is an issue, power is an issue. If you've got the world's greatest instrument, but it sucks power, through a fire hose, it might not fly. If it weighs 200 kilograms, it's probably not going to go either. So you've hit a lot of the important ones. I would have liked to see, and I think we sort of have this in SuperCam, but I would have liked to have seen this as a dedicated instrument. I would have liked to see an instrument that would let us look very far away at very high resolution. So ChemCam can actually do this with their RMI, which is essentially a microscopic imager, but it's a black and white fish lens kind of instrument. It's been improved for SuperCam, and so we're going to get some of that. But the idea that what if you could see, a kilometer away, but be able to resolve at the centimeter scale? You'd have a very tiny window, but that would be pretty awesome to be able to target things that far away and say, all right, we've got 3 weeks before we get there, and we're going to figure out, the hypotheses that we need to figure out and how it fits in. And so I'm a camera junkie, and I always feel like I'm kind of standing on my toes no matter where the rover is going. I just a few more, millimeters I'd like to see over that rise or that crater rim or whatever. So more cameras at higher resolution.
Awesome. There's a question from Joyce Sim. Thanks for the great talk. Are you currently on Sol time or Mars time, or is anyone yet on Mars time? She said, I understand people on Sol time are known as Martians while we're Earthlings.
No one's on Mars time yet. Mars time will begin, again, where to find some wood to knock. Mars time will begin right at landing, and that will be Sol 0. And that's when certain members of the team will go on to Mars time. COVID again has kind of stepped in and muddied the waters a great deal. What had happened with MSL and what had happened, with Curiosity and what had happened with Spirit and Opportunity is that the science team would go out to JPL and live essentially on campus and on Mars time, so a 24-hour, 37-minute day, and stay there for, a month or 2 months or 3 months or whatever. Of course, there's no point in doing that because nobody can go out there. And what that means is that instead of everybody kind of being in the same room or community and everybody being on Mars time, you're living with your family. And it's very difficult to wash out all of the background noise and all the background things. And it's also difficult if if you have young kids to say, okay, daddy's going to get up at 3 a.m. and you're on your own for, you can't really tell a 2-year-old that you're on your own for your own breakfast because I'm going to be sleeping from 7 a.m. to whenever. So it's not clear how every science member is going to deal with Mars time the best they can, and we're going to schedule things the best we can. And for those much smaller group of individuals who are working on the commissioning phase or working on the flight software changeover and so on, they'll probably go on to Mars time for longer. And those that can do that, they will put their time in at this time in the mission. And those that can't will probably have, you'll probably find that many of our international partners are going to work those shifts that would be late here in the U.S. and that are not necessarily quite as late if you're in France or Madrid or wherever. And so we'll be using that capability. I personally will go on Mars time for 2 weeks, starting the beginning of March, and see if my family can hack it. We'll go from there, but we're all kind of making it up as we go right now.
Yeah, I thought that might be a little different this time around. It's one of the cool things about space exploration that's also been been interrupted. And as much as I always find some of the naming cheesy, I think perhaps Perseverance was the right name for this particular rover. Actually picked before any of this happened, so it just ended up being absolutely perfect for the times.
Yeah, pretty much.
Yeah, so Chinmay has asked, could you tell us more about the landing mechanism? It's awesome. At what altitude will it start taking pictures of the surface and compare them to the global map?
Oh, those are specifics I'm not as I'm not really terribly facile with. I think we're going to start taking images with descent imagers, I don't know, within a kilometer, something like that, of the surface. I'm honestly not sure. But I can tell you that if you go to mars.jpl.nasa.gov, they're going to have the whole EDL sequence all mapped out, and they should be, I suspect they would tell you at what altitude there's going to be a rollover and what altitude the back shell is going to come off and all of that. So I didn't have a slide like that in my presentation, but I suspect strongly that if you go to that website, they will have the whole sequence.
Yeah, much like last semester when we were focusing on Titan, so we did a big thing for Dragonfly, and we sent out a bunch of clips about the science and the mission and all that stuff. So that's one of the things we're planning to send out this week. Let's see. There's another question here, which is a great question for Aileen in particular. After Perseverance and including sample return or after sample return, what's the future for Mars exploration and science?
That is a good question. So as I said, Mars sample return has been the highest priority science for Mars for decades. But I'm actually not a sample person. And so there are many other priorities for Mars. For example, polar exploration of Mars, where we believe we have a relative abundance of volatiles, is very high on the priority list. And actually, I suspect that Brittany, you probably know just about as much as I do, being on the PAC, as to what the Mars community priorities are. But there has just recently been a committee stood up and came out with a comprehensive report on what the next priorities should be. And so we're hoping that NASA will take a really good look at that report. And it includes polar science, it includes in-situ geochronology, not just for Mars, but in general. That is going to a surface, and instead of saying, well, this area is younger than this area because it lies on top, that is being sort of relative stratigraphy. The idea would be to, at the surface, pick up a sample, ingest it into some sort of instrument or set of instruments, and spit out an age, an actual age, an absolute age, obviously with error bars. But the ability to do that on Mars would allow us to put this whole stratigraphy that we have been able to put together by all of these missions into an absolute context. Actually take that tie bar and pull it over to Earth and say, this is where this happened, and at the same time, this is what was happening on Earth. So that is also a high science priority. Those are just a few.
No, that's great. So that's the end of the chat questions. Are there any questions from other folks on the panel?
Yeah, I had one question. Hi, Eileen. I'm Taylor. I'm one of Brittany's grad students. I had a question around like the motivation for, picking Jezero Crater as the landing site. Because I know there's carbonates there, like they're great fossil repositories on Earth. But I was just curious as to why like Jezero Crater was selected instead of going to say like a lacustrine environment like that has halite, which we know is also great at like preserving features on Earth. So I just was curious to understand more about that motivation.
Yeah, you brought up some of the important points of discussion when we went through the landing site selection process. So like MSL, Mars Science Lab, which is the Curiosity rover, Mars 2020 went through a community, an open community landing site selection process. And those areas that you suggested, as well as Jezero, were all kind of in the mix. Answering why Jezero came out on top is probably beyond my pay grade, but I can tell you that I think that the combination of the fact that, yeah, you have carbonates, but you also have clays, which are potentially places where you can preserve biosignatures, plus the fact that you have, for those of us who are morphologists, and you have a delta environment, which is a potential place where you would have habitability, but you also have this basement of old basalts, which are very attractive for folks who are trying to put together the chronology of Mars and kind of bracketing that period where you had flowing water. You were able to deposit deltas, but then be able to get down below and see what happened before that when Mars was more volcanic, and bracketed above, depending on whether or not we can climb, or whether we can survive long enough to climb out of the crater. I think the combination of all those things was very attractive.
Okay, thank you so much. I'm going to ask one more question. You had said earlier in your talk, you were mentioning different places on Earth, like around the globe, that we could, study, like these old rocks that we could study to learn what could potentially be preserved on Mars. In like your opinion, what places or like environments do you think are the most important for learning more about what could potentially be preserved on Mars?
And I think your question is directed towards astrobiology, and I'm not an astrobiologist, and so I have to be very careful. My background is actually in volcanology, and so I'm like, oh, let's go to the basalts, it'll be great. That's not necessarily a place where you would expect to preserve signs of life or signs of habitability, but most of my work has been in the continental United States in the desert, because as any professional on the line knows, it's far easier to get funding to go for domestic travel than it is to go for international travel. But I think Australia is kind of a crucible of having records of early Earth. And if you wanted to kind of have a lot of bang for your buck, that might be a place to go. You have very, very old rocks. You have areas where these stromatolitic fossils are preserved, and you have a long history in the rock record. So I'm all for context, and so if I were funded to go wherever I want, that's probably where I'd end up going.
Okay, sweet. Thank you so much. And I really, really enjoyed your talk.
Oh, thank you very much.
Frances, any closing remarks?
No, except that I'm really excited about Perseverance finally landing next week, and I'm sure that Aileen is as well. And that's yeah, thank you everybody for tuning in today. And as we mentioned in the beginning, this is just a kickoff for the first Space Science Week at Georgia Tech, and so we'll be sending out a lot of emails with information about Perseverance and a lot about the space science community here at Georgia Tech. And so let's thank Aileen again for taking her time to come and talking to us. And so thank you.
Thank you very much. It was a pleasure.
Yeah. Yeah, that's all from